All right, official good morning to all of you 3 showing up. Thank you. Okay, so first things first, the final exam schedule is posted, and what I might try to do is, oh, I lost it, didn't I? I was gonna send you guys the link, but if you just Google Okanagan College final exam schedule, you'll find it. So pretty nice to know when our final exam is. And what's even better is that it's early on in the exam period. So, woo-hoo. So our final exam is on Saturday. So there are Saturday exams. I'm not sure if you have written exams with the college yet, but there are Saturday exams. They just start a half hour later. It's really weird. But no Sunday exams, just Saturday exams. So just be aware that that is a possibility. Saturday, December 12th, from 1:30 to 4:30. Yeah. So that's good to know. That's when our final exam is. Whee! But a while yet till we get there. But it's just nice to know you can mark your calendars and kind of plan around it for leaving or whatever. So, hey, your birthday. Tushar's birthday. I'll see if I can find an appropriate, oh, I only have this one. Cute. We have to remember that. What a way to start your birthday. Nice. I went through your test once, so thank you for sending your work. What you'll have found is that what I did was, if there was a question that didn't have a response, I went through and I looked at your written work to see what your answer would have been, and then I filled it in and gave you marks accordingly. For some of you, that was a lot of marks, so you'll want to make sure that you work on submitting your answers, right? So I know that was, it was our first test, so we're just learning, we're all just learning. But so we're gonna use the same method for testing for the rest of the tests. So, so just keep that in mind, right? But I want you to keep sending me your work so that I can just go through and make sure that you get all the marks that you're supposed to have, right? And so I went through all your tests, and your grade is adjusted on WebAssign if necessary, right? If it was needed. A lot of you did really well, and so I'm really proud of you. And so I'm really impressed, actually, that you were able to work through that test and do so well. So if you feel like, oh, that wasn't my best test, that's okay. We have more tests, right? And so just keep improving, keep working on these things. And I know it was our first time doing that sort of test, so next time you'll know more what to expect. And as long as you're improving, and if your final exam is better, then I can do some shifting on the weights of the grades. So, but I don't know that until, or I can't do that until all your tests are written, right? And so but I know that you want to have a good grade and I want you to have good grades. And so I kind of have a look at it at the end of the term. Okay. So as long as you're improving and you're doing better on each test, then that's a good thing, and we can keep that in mind. I'll keep that in mind when I adjust your grades. Okay. So let's see here. We're going to start functions part 1. I am going to post part 2 as well, because the previous lecture that I just did, we got way further than I thought we would. So, and that's, well, maybe not as far as I thought we would, but hoped we would. But so we're gonna chip away at functions part 1, and then there's a functions part 2. And so we'll see how far we get this week, and I'll adjust it at the end of the week. Okay. So we're starting chapter 2 is on just functions. What's interesting about chapter 2 is we're just going to redo a lot of the stuff that we did in chapter 1, except in terms of functions instead of just expressions or equations. So now we're talking about functions, but the idea of everything that we've talked about so far, we've talked about linear graphs, we've talked about domain, we've talked about all these different things. Now we're just going to combine them and talk about functions. So section 2.1 is just called functions. Okay. So if you go to your, functions part 1 handout, okay. A function is any sort of machine. So often when you're starting to talk about functions, we talk about it being a machine, but it really just takes some input and produces some output. So the function f is the machine that does it, and f can be complicated, it can be easy, but we give it some input x and it produces some output f of x. And so the definition of a function is a little bit wordy, but we'll copy it anyways because it's official. So a function, f, so f is just the name of the function, the name of the machine, is a rule that assigns to each element x in a set A exactly one element called f of x in a set B. So in kind of simpler terms, right, a function, takes one input, x, hey, what happened there? One input x and returns one, and that's important, one output f of x. Okay. So that's kind of a simpler way of saying this kind of wordy thing, but it just takes one input and returns one singular output. So let's have a look at what that might look like. So if we copy this nifty little graphic here, okay, keeping in mind that, okay, so if we take one input, it can only return one output. So if we have this machine f that takes a 0.1 and gives an output of 20, okay, that's safe. 2 gives us 20 as well, that's allowed. So we're allowed to arrive at the same output for different inputs, right? But it takes one input and returns one output. So one value from the inputs can only go to one value of the outputs, okay? Whereas, so this would be a function because each of the inputs maps to only one output. Here, this is not a function because the input of 2 goes and gives us 20 or 30, depending on what's going on. So this is not a function, and that's going to be important when we look at, you know, what are functions, what can we do with functions, etc. So here, this is not a function. Oh, maybe I'll give myself another line. This is not a function since x equals 2 gives f of x equals to 20 and 30, right, which can't happen. So that's what a function is. And notice that we're using this function notation. So function notation, I want you to get really comfortable with function notation. Anything where we have something smushed up against brackets, usually read those as of whatever's inside the brackets. So f of x. So here, for function notation, you read this as f of x. Okay. G of x, g of x. You could even do something weird like dog of x. You have some function dog and it takes some input x and it gives you some output dog of x. Dog of x. If you go into statistics, for example, we often use e of x. And so just getting used to reading these functions is going to be really helpful. Notice that, okay, everything inside the brackets, that's your input. And then the total thing is your output. So here, the input, and then actually, let's put this on a different line here. If we have f of x, x is the input, and f of x is the output. Okay. If we think about it as a graph, right, we can graph x, f of x coordinates. And the reason for that is if you just have x, then we can talk about f of x is the same as y, right? So for our purposes, we can use f of x and y interchangeably. So that could be useful, right? If you're having a hard time with f of x, as long as you think, okay, well, if I give it some x, it gives me some y back. So in terms of a graph, right, an xy coordinate grid here, if I give it some x equals a, for example, right, then if I've got my graph here like this, x equals a puts me at this point on the graph, right? So this is my function. So here, f of a equals y, right? Or just in general, f of x equals y. Here, I've forced my x to be a just to be kind of clean about it. So I give it some input a, and it spits out some output f of a or y. Okay. So just keep in mind that all of these, right, we write as an input output coordinate pair. So we always get an input output coordinate pair. Right, if I give it some x, it's going to give me back some f of x, which we have been calling y up until now. Oops, I want the eraser. Clean this up a little bit. There. Okay. So we're going to use those coordinate pairs. We could use those coordinate pairs to draw graphs. Later on, I think it's in section maybe 2.2. Yeah, we're supposed to draw graphs by plotting points, but I'm just going to encourage you to use Desmos instead because it's going to make things a lot easier. So, but we do need to be able to evaluate functions. And so let's go steal some of these questions and see what we can do. Okay, so let's see here. Let's start with 19. Nice and slow, right? So we're given a function x squared minus 6, and then we're asked to find f of -3, f of 3, f of 0, and f of 1/2. Right, so it's just asking us to put in these inputs and figure out what the output is. So 19, f of x is x squared minus 6, and we're asked to find f of -3 first off. F of -3, wherever I see an x, I'm going to plug in -3 as its own thing, right? Later on, when we're plugging in bigger things than just one number, you'll definitely want to have these things in brackets so that when you plug them in, you treat them as one thing. So -3 squared minus 6. I want you to double check something, right? Because -3 is what's squared. So you don't want to have -3 squared, right? There's a difference. So you want to make sure that your calculator, when you do -3 squared, you should get +9. In fact, whenever you square or take the even power of a number, you should get a positive value back. It only returns positive values. So you want to just make sure that when you do -3 squared, you should get 9, not -9. So you get 9 minus 6, which is 3. How about f of +3? So now this is going to be 3 squared minus 6. 3 squared is also 9, right? So I get 9 minus 6 again, which gives me 3. This is allowed because I'm giving it different inputs, but I'm getting the same output. Because they came from different inputs, that's allowed. Will it not be, oh, I chose this easy one first. I think you're potentially looking at this one.
No, I'm just wondering that like the f minus 3 will be minus 3f, and then minus 3 will be divided by the other 3.
Oh, are you looking at this one, the first one, 19?
Yes. Like you solved my f minus 3 and you got it equal to 3, but like it's if we multiply f with minus 3, it will be like minus 3f, then minus 3 will be divided by 3.
Oh, but so here, I think what you're doing is you're putting this -3 outside.
Yes.
But it's your input.
Oh, okay. So I don't need to just look at it.
Yeah, so when it's inside those brackets, you just use it to replace x. So here, so this is different from -3 times f of x. This,
Okay.
yeah, this is the function at -3. So you
Now
get
I get it.
-3 squared minus 6.
Okay, thank you.
No problem. Good. Yeah, it would be different if this was outside. Then, of course, yes, then you would have to divide by 3. Good. But because it's inside these brackets, we plug it in as the input. Okay, good, 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 good. Let's do, what's the next one? F of 0. So f of 0, keep it on the same page here, 0 squared minus 6 puts me at -6. F of 1/2, need to be a little bit careful, right? And so here, I guess I'm gonna need more room, so f of 1/2 is 1/2 squared minus 6. Okay. If you've got a trusty calculator, right, especially one like this that gives you the exact answer, it's going to be a lot easier, right? So it might be nice to find, if you are able to find an app that has a nice scientific calculator. They're usually free. I downloaded the Desmos Calculator App, and you know what? I'm going to try it on this one. So the Desmos Calculator App is that the third root of 27 one. I don't have a pointer on here, so it's this one. And this is the calculator version. So there's a graphing app and a calculator app. And I just wanted to try the calculator app to see. It's pretty good. It's pretty good. So what we had was we had bracket 1/2 and bracket, oh, make sure your brackets are, step it out and bracket. And then I want to square that. And then -6. So make sure it looks like what you expect it to look like. And let's see here. Okay, so it seems like if you hit this little dot, oops, it'll convert it from the exact answer to the approximate answer, but it seems to default to the approximate answer. So I want the exact answer, -23/4. So we can, use your calculator to say, okay, well, this is -23/4, right? Using a calculator such as the Desmos Calculator app. Okay. One thing to keep in mind, okay, because we will have to differentiate between the exact answers and the approximate answers. Approximate answers are always the ones with the decimals. So here, this is what we would call the exact answer. And then to denote the approximate answer, I'm going to use squiggly equals. I should make them look a little bit better. Squiggly equals -5.75, I think it said. Let me just confirm. Yeah, -5.75. This is the approximate answer. We're always going to give the exact answer unless I specify that I want you to round to 2 decimal places, for example. Right? In this case, there's a bit of a gray area because this is the number, so it is exact. But just as a rule of thumb, I want you to start thinking, okay, if I've got decimal answers, it's really an approximate answer, whereas this is the exact answer. So you're definitely allowed to use your calculator for these things, right?
I have a question here.
Sure.
How do you put this approximate sign in WebAssign?
Well, WebAssign will ask you for the decimal approximation. So it'll say round your answer to 2 decimal places, for example.
But like sometimes it says, I remember the last time it was like write the exact decimal value, but like that was like no, it doesn't accept sometimes.
Okay. If you're able to find an exact example, then you can use the message instructor. I'm not always on WebAssign, of course.
Yeah.
But I do get those messages every now and then. So, or I check them, I guess, when I'm on there. So if you're able to find one that's acting weird, then use the message instructor and then it'll show me the question and I can try it out. That would be really good.
Thank you.
Do that. Awesome. Yeah, because I want to know about those things. It's good. So it might be in the symbols, but I don't think you should need to use it. But anyways, I'd love to see one. So, or instead of using your calculator, you could solve this by hand. I say by hand because you'll probably end up using your calculator at some point. Right, and so f of 1/2 is 1/2 squared minus 6. Here we're using exponent laws that we learned about. We're subtracting 2 fractions, which means we have to have a common denominator. So it's incorporating all those things from chapter 1 that we spent so much time working on. So this I can rewrite as 1 squared over 2 squared, which is 4, minus 6. Now I'm subtracting a fraction. 1 over 4 is a fraction, 6 is a fraction, 6 over 1 is a fraction, right? And so I need a common denominator. And I'm going to use a common denominator of 4 times 1. This I don't need to change, right? 1 over 1. But I do need to multiply by 4 over 4. So I get 1 minus 24 divided by 4, putting me at negative 23 over 4, which is approximately equal to negative 5.75. Sorry, I just need to. I know, it's so runny. Bad news, right? All right. At least I'm here and you're there. Okay. So these ones weren't that bad, right? Evaluating functions. But let's go back and pick kind of a harder one. And which one do I want to do? Maybe I want to do, let's do 22. So we'll do 22. In fact, I'm just going to copy and paste it here. Oops. Copy. So I have it on the right page. Oops. There we go. Okay, so I've got h of x is x squared plus 4 divided by 5. So these first few are fine. I'm just plugging in 2 and negative 2 and evaluating these things. And then things get weird, right? And then I'm just plugging in a. So h of x versus h of a, all I'm looking at is I'm swapping the x's for a's. Negative x Then I can get really weird and I can plug in a minus 2 for x, remembering that whatever you're plugging into your function, it has to stay together. So the a minus 2 is one thing. So let's try these. H of 2 is x squared plus 4 over 5. But if I plug in x equals 2, what I get is I get 2 squared plus 4 divided by 5, which, because I've got this invisible page break here, I'm just going to write it here as 8 over 5. I'm going to leave it in exact form. H of negative 2 is going to look a lot the same, right? In fact, negative 2 squared plus 4 over 5 puts me at 8 over 5 again, right? Because negative 2 squared is 4. 4 plus 4 is still 8 over 5. And so those two, not bad. Let's look at H of A. H of A is going to be a squared plus 4 divided by 5. There's nothing more I can do there, so I just have to leave it like that. Let's look at h of negative x. Okay, so h of negative x is negative x squared plus 4 over 5. Notice that you have to treat the negative x as one thing, right? So technically negative x squared is just going to become x squared, right? Because it's going to be the positive version of itself. But I would probably just leave it like this. I would just leave it as is, can step away. It depends on what you're going to do with this thing later. Sometimes it's easier to simplify, sometimes it's not. So now, this is kind of the one that I really want to do. H of a minus 2, remembering that a minus 2 is one thing. So h of a minus 2 is a minus 2 squared plus 4 divided by 5. Being careful, right, because a minus 2 squared is a minus 2 times a minus 2. So we're going to expand this and see if we're able to cancel anything. So what we get is a minus 2 times a minus 2 plus 4 divided by 5. You could definitely leave it like this, but I just want to show you and emphasize that a minus 2 squared is a minus 2 times a minus 2. So we get a times a is a squared minus 2a minus 2a plus 4, and then plus 4 again, divided by 5. I can simplify this a little bit, right? I get a squared minus 4a plus 8 divided by 5. Okay. And that's it. So next, the last one we want to do is h of root x, remembering that the root of x is one thing. It's easier to do because it looks like one thing, right? But you have the root of x squared plus 4 divided by 5, remembering that if you square a square root, they kind of undo each other, so all you're left with x is x. So this becomes x plus 4 divided by 5. Okay. Good. So we need to be able to evaluate functions. We're going to keep doing that. Let's talk about piecewise defined functions. So piecewise defined functions look like this. So I'm going to snag these in here. Ding, ding, ding. Good. So what's going on here is, depending on the input, right, we're going to have different functions that we use for the output. So if x is less than 0, f of x is going to be x squared. If x is greater than or equal to 0, notice that there can't be any overlap, right, in these ranges, because then the function wouldn't work. If x is greater than or equal to 0, then f of x is going to behave like x plus 1. So it just depends on what value of x you give it to figure out what the function is and what the output is. We've seen piecewise defined functions before. We didn't call them that, but the absolute value function, right, is negative x if x is less than 0, and it's going to be just x if x is greater than or equal to 0. So we've seen piecewise functions, we just haven't called them that necessarily. Okay. So we can do one from here. Let's do 33. Keep things interesting. Okay. So 33 says that the function, so the output, is going to be x squared plus 2x if x is less than or equal to negative 1. Okay. Between x is negative 1 but not equal to negative 1, if it's equal to negative 1, it bumps you up to this first bracket, right? If x is between negative 1 and 1 inclusive, then f of x is just x, right? And then if x is greater than 1, but not equal to 1, f of x is just constant at negative 1. So I'll put it here, 33. F of negative 4. So if f is negative 4, got something like so weird because I just brushed my teeth, but anyways, I don't know. If x is negative 4, then x is less than or equal to negative 1, right? Negative 4 is less than or equal to negative 1. So the function that I'm looking at is x squared plus 2x. So here, I'm just going to make a note. X is less than or equal to negative 1. So f of x is going to be x squared plus 2x. So f of negative 4 is going to be negative 4 squared plus 2 times negative 4. Negative 4 squared plus 2 times negative 4. I think this is the first time that we've seen two different values of x, or two different inputs, or the input in two different places, I should say, right? But wherever you see an x, you're going to replace it with negative 4 and then evaluate. So negative 4 squared is 16, and then 2 times negative 4 makes minus 8. So we get 8. 16 minus 8 is 8. The next one, right, a little bit tricky when we've got this fraction, but just remember, if you do 3 divided by 2 on your calculator, right, that'll give you a good idea of on the number line where is 3 over 2. So 3 over 2 on your calculator, whoopsies, not close, 3 divided by 2 on your calculator is 1.5, right? So now you want negative 1.5. So you can absolutely convert your fractions to decimals to put them on the number line to see where things are. And so here, f of negative 3 over 2 is the same as f of negative 1.5. So still here, x is going to be less than negative 1, right? Negative 1.5 is less than negative 1. Remembering that things are kind of opposite of how you want them to be on the negative side of the number line. So here again, f of x is going to be x squared plus 2x. So we get negative 3 over 2 squared plus 2 times negative 3 over 2. Okay. noticing that you've got a fraction and a fraction. If you're doing these things by hand, then yeah, you should probably go ahead and find the common denominator and things like that. But I'm just gonna use my calculator, my trusty calculator, making sure I have my brackets where I need them to be -3 divided by 2, and then square it, plus 2 times -3 divided by 2 in brackets. Puts me at -3 divided by 4. I'm going to confirm that in Desmos, right, using that Desmos calculator that we have. Clear all, good. And so I've got, where was it? Bracket, -3 divided by 2, step it out, end bracket, squared, minus, where is it? Sorry, plus 2x plus 2 times -3 divided by 2, end bracket. And I get -3 divided by 4, which is what I found on my calculator as well. Right, so like -3 divided by 4 as the exact answer, -0.75 as the approximate answer. Now, good. Just for practice, maybe, you could go ahead and you could find the common denominator, and you can make sure that you get to here. But I'll leave that for you to do. Okay. F of -1. So now f of -1, if x is less than or equal to -1. So here, this is the range where it's equal to -1. So this is still the function that we're using when x is -1. Is going to be -1 squared plus 2 times -1. 1 plus -2, so that's 1 minus 2, -1. Thanks. Let's move on to f of 0. Finally, our function isn't going to be x squared plus 2x anymore. If x is 0, then x is between -1 and 1, right? So 0 is right in the middle of that. And so x is just going to be our output. So f of 0, right? Here, just making a note that x is between -1 and +1. So f of x is just x. F of 0 then would just be 0. F of 0 equals 0. Finally, dealing with f of 25. 25 is when x is greater than 1. So for any value of x greater than 1, it's just the output is just -1. So it doesn't care what the input is, as long as it's greater than 1. F of 25. So here, x is greater than 1. So f of x equals -1. Which means you get the same output regardless of the input. So f of 25 is -1. Dealing with function notation and just kind of doing some practice with function notation, we can talk about things like the net change. The net change of a function. It's on the next page. So the net change in the value of function f as the input changes from a to b, where a is less than b, then what we can do is we can find the net change by finding f of b minus f of a. So what this looks like is kind of in its most general form. We've got our x and our y-axis, and I'm going to put a is less than b here. And I'll have my function might look something like this. And what I've got here, these points are at a f of a and b f of b, right? The function evaluated at each of these points. So we get f of a and, see if I can trace across here, f of b. What this is saying is that the net change is just the change from here to here, which, remember, if you go back to finding the distance between these 2 points, you would find this minus this, right? That's your net change. Because we're allowing for negative changes, we don't take the absolute value, but otherwise it's the exact same as when we were finding the distances between 2 points. But now we're working on the y-axis instead of the x-axis. Okay, so here, this distance, this is the net change. Something to keep in mind is that you could have something that looks like kind of weird. So here we've got a and b, and even if you've got some function that looks like, actually, let me start again. Still not exactly what I wanted to show. Keep it together. I'm like, wee. Okay, something like this. Well, something like this, here, f of a, and here, f of b. We've got a negative net change, right? Because it actually went down, but the overall change doesn't take into account. So don't be tempted by this huge upswing, right? Between a and maybe this point, your net change would be huge, right? But between this a and this b, the net change is just the distance between f of a and f of b. So here you would have a negative net change. Later on, we're going to talk about rates of change. So that's when we start incorporating. We need to look at the net change divided by the change in the x-axis. But for now, we're just talking about net change and how do we calculate it with different functions. So let's have a look at some of these examples. First thing we notice is that we've got these different names, and I haven't really been paying attention actually. I think they've all been f of x so far. But notice that f of x, g of t, h of t, that's allowed. T is now just the name of the input, right? So g of t takes an input of t, and that's the variable that we have in this equation. H of t, the function is called h, and the input is called t, but it behaves the same way. T would just be on the x-axis. T is usually for time. So then time, of course, would be increasing as you move out. Let's have a look at, let's just do the last one, right? Get right into it. So we want to find the net change in the value of the function between -3 and 6. So h of t, where t squared plus is t squared plus 5, and we want to find the net change from -3 to 6. So 42, A is -3 and B is 6. The net change is f of B minus f of A, which is going to be f of 6 minus f of -3, making sure that you keep all the negatives where they're supposed to go, right? F of 6, now we need to, again, keep our kind of wits about us here. 6, f of, oh, sorry, f, not here, h. Oops. Our function's called h. In general, we use f of b minus f of a, but we've replaced our f with h and our x with t's. H of 6 minus h of -3 is what we want to do. So h of 6, and what I'm going to do, h of 6 is going to be one of these, and also h of -3 is going to be another one of these. So I like to keep them separate with square brackets until it's safe to remove those brackets. So what I'm going to do is I'm just going to move this down here because I definitely needed more room than I gave myself. Classic. So h of 6 is going to be, I'll just remind myself that h of t is t squared plus 5. H of 6 is 6 squared plus 5, square bracket, minus h of -3, -3 squared plus 5, square bracket. Six squared is 36 plus 5. Treat that as one thing. Minus -3 squared is 9. 9 plus 5, treat that as one thing. So you get 36 plus 5, which should be 41, minus 9 plus 5, which is 14. Which, 41 minus 14, 27. Just double check. Right? And always just use your calculator. There's no sense in making silly mistakes. Good, 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 good. So let's talk about the difference quotient. The difference quotient comes up in calculus, so we use it as a way to work with functions, right? Plugging values into functions in pre-calculus, but what we're doing is we're building up to when we need it in calculus. So if you plan on taking calculus, you'll need to be able to work with the difference quotient, and here it is. We don't need to know what it is or what it really does, even though you could pick it apart and figure it out. But the difference quotient here is, I'm just going to bring it in. The difference quotient is f of a plus h minus f of a over h, where h can't be 0 because we can't divide by 0. So that kind of goes without saying. So I'm not going to say that anymore, but of course h can't be 0. So the difference quotient is used in calculus but we use it as an exercise in working with functions. So it's good to get used to how these things work, right? And so the difference quotient, I'll put it down here. Is f of a plus h minus f of a divided by h. Okay. Now, this on its own, f of a plus h, given a function, we should be able to find that. That's not so bad. We've already kind of done something like that. F of a is easy, right? You just replace your x's with a's and then off you go. The tricky part is combining these, f of a plus h minus f of a, and then dividing by h. What's nice about the difference quotient is this h that's in the bottom, eventually, if you've done things correctly, it will cancel out. So that's really nice about the difference quotient is if you've done things correctly, things will cancel out and it will simplify and you'll be able to get rid of this h. Okay. Not all h's, but this h in particular will cancel out. So here, right, it will be easier to find f of a plus h and f of a individually and then combine to find the final difference quotient. Okay. So let's see, which one should we do? Let's do 44. Practice with some squares. So we have 44. I'm just going to copy it from here, my side notes here. 3x squared plus 2. So if we first find f of a plus h, it's going to be easier to find f of a. So maybe let's start there. F of a is going to be 3a squared plus 2. Right, wherever you see an x, you're going to replace it with a. Fine. F of a plus h is going to be 3 times a plus h squared plus 2. Keeping in mind that a plus h squared is a plus h times a plus h. So you have to expand that out and then hopefully simplify. So what we get is we get 3 times a plus h times a plus h plus 2. Okay. So this becomes 3 times a squared plus ah plus h squared and then plus 2. Or if you wanted to skip straight to 3 times a squared plus 2ah plus h squared plus 2. That's totally fine. My goal is to try to simplify this as much as I can before I plug it into the difference quotient. Right, so what I'm going to do is I'm going to expand this 3 onto each of these terms. You don't want to forget about a term, right? Everything has to be multiplied by 3 before you can get rid of these brackets. So you get 3a squared plus 6ah plus 3h squared plus 2. So now, there's nothing more I can do here. There's nothing I can simplify or kind of collect like terms or anything like that. So I guess I'm ready to plug it into the difference quotient. So now I'm ready to find f of a plus h minus f of a divided by h. Okay. Being really careful, f of a plus h, that's this whole thing. minus f of a, that's this whole thing. So you want to keep them, I always use just big square brackets to denote that, okay, here's f of a plus h and here's f of a. So this becomes 3a squared plus 6ah plus 3h squared plus 2 minus 3a squared plus 2. Notice that this minus is on the outside, right? And what looks really exciting is, hey, it looks like I'm going to be able to cancel a couple of things here. And that's always kind of what happens. Divided by h. So now what I'm going to do is I'm going to expand these out. So I'm going to get rid of these brackets. The brackets on here don't really do anything. It's just for me to visualize that f of a plus h minus f of a. But I am going to expand this negative into these brackets to get rid of these brackets. So I get 3a squared plus 6ah plus 3h squared plus 2 minus 3a squared minus 2. Make sure you put that negative on the 2 as well. Divided by h. Do not get sloppy and forget about that divided by h. It's going to change everything if you do. So just always put it in there, right? I don't want to see you get lazy. 3a squared minus 3a squared. That's going to go away. Same thing with plus 2 minus 2. That goes away. So what I'm left with is I'm left with 6ah plus 3h squared divided by h. What's really nice and kind of what I was hinting at before was I'm able to pull out one common h, so factor out an h, which I'm able to cancel with the h in the denominator. So I get h times 6a plus 3h divided by h. Cancel, cancel. All I'm left with is 6a plus 3h. And then you're done. That's the difference quotient. So, let's do another one. I just want to make sure how we're doing here. Okay, let's do another one because these can be really tricky. Let's do one with a fraction. And if you kind of look ahead, you're going to have a fraction minus a fraction over h. So it's going to be pretty nasty. But that's why we spent so much time dealing with all those fractions earlier in chapter 1. So we're ready to take on 48. Let's see here. I'll copy it out. 48 says f of x is 2x over x minus 1. Notice that we've got two values of x now, right? X in the numerator, x in the denominator. So wherever you see an x, you're going to replace it with whatever the input is. So first thing we're going to do is we're going to find f of a. Well, that's easy enough. 2a over a minus 1. So replace your x's with a's. That's easy. F of a plus h, a little bit trickier, but not bad, right? So now wherever I see an x here, I'm going to replace it with a plus h. So I get 2 times a plus h divided by a plus h minus 1. Okay. I can expand these to get rid of the brackets. Remember, you want to simplify f of a and f of a plus h as much as you can before plugging them into the difference quotient. So this becomes 2a plus 2h divided by a plus h minus 1. So now f of a plus h minus f of a divided by h, making sure, so now I've got a fraction minus another fraction. So I'm going to give it lots of room here, right? two lines for the first fraction minus the second fraction, and then over h. So, and then square brackets again all around. So 2a plus 2h divided by a plus h minus 1 minus 2a over a minus 1 over h. Okay. Fraction minus a fraction, even though we don't want to, we have to find a common denominator. And remember, I'm just going to use these two multiplied together as my common denominator, which means I have to multiply this fraction by a minus 1 over a minus 1, and this fraction by a plus h minus 1 over a plus h minus 1. So what this becomes is we get, and I'm going to give myself lots of room here, is I get 2a plus 2h over a plus h minus 1, and then times a minus 1 over a minus 1 to get that common denominator, minus 2a over a minus 1 times a plus h minus 1 over a plus h minus 1. Okay. My common denominator is just this a plus h minus 1 times a minus 1. I tried it in my earlier class, I expanded it. It didn't really take me anywhere, so I'm going to keep them factored like this. But you can try it, try factoring it out or expanding it out. It doesn't change anything. So let's see here. This is all over h, don't forget. All right. Eventually we're going to have a fraction over a fraction, h over 1, right? And then we can flip and multiply to simplify things a little bit. So this becomes 2a plus 2h times a minus 1. Minus 2a times a plus h minus 1 over a minus 1 times a plus h minus 1 all over h. Okay. So what I'm going to do is I'm going to expand these out, and I'm going to hope that maybe some things will cancel out up here, right? That's my only hope for things that might cancel out. So here we go. 2a squared minus 2a plus 2ah minus 2h minus, and then I'm going to put it in brackets here because I'm going to expand first and then bring that negative inside. I don't want you to do both at the same time unless you feel really, really confident. Okay, so 2a squared plus 2ah minus 2a. Okay. All divided by a minus 1 times a plus h minus 1 all over h. Okay. Already I'm getting excited because I'm seeing 2a squared minus 2a squared, that's going to go away. 2ah minus 2ah, that's going to go away. Negative 2a plus 2a is going to go away. So a lot of these things are going to cancel, right? Which is really, really nice and fun to see. So this becomes 2a squared minus 2a plus 2ah minus 2h minus 2a squared minus 2ah plus 2a over that common denominator a minus 1 times a plus h minus 1 all over h. Let's cancel some stuff. 2a squared minus 2a squared. Negative 2a plus 2a plus 2AH minus 2AH. All I'm really left with is negative 2H here. So now this becomes negative 2H over A minus 1 times A plus H minus 1. Now I'm going to emphasize that I've got a fraction over a fraction. A fraction over a fraction, I'm going to flip the denominator and multiply, right? And so here I've got over H over 1. Okay, so this becomes negative 2H over A minus 1 times A plus H minus 1 times H over 1 becomes 1 over H. And all of a sudden I'm able to cancel this H with this H because I'm multiplying all these things together. So finally, we're just left with negative 2 over A minus 1 times A plus H minus 1. And whether you wanted to expand this out or leave it factored, it doesn't matter. Like I said, I tried to expand it in the class before this. It didn't really get me anywhere, so that's why I'm not going to do that now, but it doesn't matter. They're the same. Nice. So that one's tricky, right? But we have to remember, how do we deal with fractions? How do we subtract fractions? How do we deal with a fraction over a fraction, right? All these things that we've already been practicing so much. Okay. So the last thing in this first section is just a refresher on the domain of a function. The domain of a function are all the possible inputs, right? And we can also talk about the range of a function. Here in the exercises, you're only talking about the domain, but later we'll talk about the range as well. So I'm going to say, recall from, because we've already talked about the domain, we didn't talk about the range, I think. I don't think so. In section 1.4, we talked about the domain, and we talked about things like, well, we can't divide by 0, and we can't take the even root of a negative number. So recall from section 1.4 that the domain of a function, or that the domain, we didn't call it a domain of a function then, right? But the domain of a function is all possible input values, right? Input values, which mean x. So I'll just say input values of x. We have to remove values of x that make you divide by 0 and take the even root of a negative number. So our domain must exclude values of x which make you divide by 0, right? That's not allowed, but also take the even root, square root, fourth root, sixth root, whatever, take the even root of a negative number. Okay. And sometimes we just restrict the domain, even if there aren't any complications. We just say, okay, between 0 and 6, for example. So sometimes we just restrict the domain just because it makes it easier to think about. But definitely in your domain, you have to exclude values that make you divide by 0, and you can't take the even root of a negative number. You can take the odd root of a negative number, as we'll see, but for us, This is just a little refresher. So what I want to do is, I just want to steal some of these. Nothing crazy. Where's one that I wanted? Oh, maybe I'll do all of them. The one I want is a combination of these, right? So where I'm dividing with a value of x in the denominator and also has a root that I have to take care of. So the first one, or kind of a nice one that I see here, is 70. So 70 says f of x is x squared divided by the root of 6 minus x. So first thing we have to do is we have to make sure that we're not dividing by 0. So that means that the root of 6 minus x can never be 0. Okay, so first thing, let's call this criteria number 1 and criteria number 2. 1 means that the root of 6 minus x cannot be 0. Right? I can't divide by 0. So the restriction on x then is going to be, I can solve for x here. I can use this not equal to as if it's an equal sign. It's when we have inequalities we have to worry about dividing or multiplying by a negative number, which we've talked about. 6 minus x cannot be 0 squared, right? Squaring both sides to get rid of that square root. And then solving for x, 0 squared is just 0, so 6 can't be equal to x, which if you just double check, 6 minus 6 is 0, 0, square root of 0 is 0. And that's what's not allowed. So it makes sense. In our domain, x cannot be 6. On top of that, we also can't take the root of a negative number, right? So 6 minus x has to be greater than or equal to 0. So for our second criteria here, we're saying that 6 minus x has to be greater than or equal to 0. In general, right, we're allowed to take the square root of 0. The only hiccup is, but we've already taken care of it, is that the square root can't equal 0. So if you wanted to, you could summarize both of these as 6 minus x has to be greater than or greater than 0. So what we get is adding x to both sides, 6 must be greater than or equal to x. So the domain here is the combination of these two things. So x can't be 6 and x has to be less than or equal to 6. Well, it can't be equal to 6 if we're doing a combination here. So therefore, the domain is the combination of these criteria I was going to say criterion, but I'll just say criteria, which is that x has to be less than 6. Rewriting this as with x on the left-hand side, but the inequality just follows the x, right? And so the less than is pointing towards the x, so x is less than 6, because x can't be equal to 6. Nice. So that's a little refresher on the domain. I know you had to do domains on your test, so but they were a little bit easier than what we're doing today. We've seen stuff this hard, but we're just kind of getting warmed up. Okay. So next stop, we're talking about, in section 2.2, we're talking about graphing functions. This is where they talk about graphing a set of ordered pairs. So if you have a function like x squared minus 4, what you can do is you can just pick values of x and see what the output is, plot those points, and then make a graph that way. I actually don't really like doing that. I would prefer it if you wanted to do that, then sure, that's good. That's a good skill to have. But I want you to check it with Desmos. So even if you're graphing by just plotting ordered pairs, I want you to check your graph using Desmos. So put this new section down here, 2.2. It's called graphs of functions. Okay. We can, and I'll kind of underline can, we can graph functions. We can graph functions by plotting ordered pairs. Oh, ordered, by plotting ordered pairs. Can't imagine how many of those slips I have that I don't notice, but anyways, I think you know what I mean. We can graph functions by plotting ordered pairs. And connecting the dots but you should always check your graph in Desmos, right? But you should always check your graph in Desmos. So this section, right, the exercises that I've included for you to work through, they get you to plot points, make a table of values, so plug in different values of x and then figure out what the f of x is, or the output value of x is, or the function is. Let's see here. But what I really want you to look at is the bottom graph, or a table rather. And so it will be really useful, to be able to recognize the general shapes of some common functions. So to be able to recognize, the general shapes of some common functions. Right, just to know what to expect when you're potentially graphing these things, right? So here, I'm going to copy this in here. Whee! And I want to talk about some of these. We've seen a lot of these already, right? We know that a linear function is anything that has y equals mx plus b, but remember y is just f of x. F of x is mx plus b. That's a linear equation, so it's just going to give you some sort of straight line. It can be horizontal, or it can be on a slant. It can be positive, it can be negative. We've talked about linear functions already. You can also have power functions. In general, even powers give you this kind of this parabola shape, and the higher the power is, the more it kind of like plops down on the x-axis, right? So it just becomes heavier on the x-axis. For odd powers, we get this kind of wing shape. And again, for the larger the power gets, the more it just kind of lingers on the x-axis. Right, so knowing this general shape is really useful, right? So if you have this even power of x, then you know overall this is going to be the shape. There could be weird stuff going on in the middle here, right? But overall this is the shape. If you've got an odd power of x as your highest power, then the end game is going to look like this, right? The middle section might behave differently, right? But notice right here, it's giving us the domain as well. So knowing what these graphs look like also tell us something about the domain. Here, the domain is any real number, so all real numbers. All real numbers, we can plug in all real numbers into these power functions. For the root functions, square root, for example, notice that the graph starts at x equals 0, right? And so we already know that we can't take the square root of a negative number, and that's indicated on the graph. So the domain is that x has to be greater than or equal to 0. Whereas if we take the third root or any odd root, it'll look kind of like this, where it's basically this little guy. Well, it's kind of like flipped and mirrored, but the general shape looks the same. Back to an even root, can't take the even root of a negative number, so it's shown here. You can have a look at the reciprocal, the absolute, well, knowing that the absolute value is this V shape, that's really helpful. But in general, recognizing these first three is going to be really, really useful. So focus on these for now. Right, so those little starred ones, you want to make sure that you focus on those. Okay. So even if you have, so specifically power functions, the highest power of x is going to dictate the end behavior, and then you could have some other behavior inside, and we'll see that later on in an example, but if I pick the right one. But for now, these are just really good to know. So when you're looking at these problems here, right, knowing what the third root looks like, right, knowing that it looks like this, that's going to help you pick points and plot points and just kind of know how to connect these dots, right? Because usually there's some sort of curvature. So there's more on piecewise defined functions. I'm just going to leave that for you to work through. I'm not too concerned about those. As long as you're able to evaluate piecewise defined functions, then I'm happy. So if we have a graph, then, so if we have a graph of something, some relationship, then we can use what's called the vertical line test to see if it is a function. So there are graphs like this that exist, but they're not graphs of functions. So we need to be able to say, okay, that's a function. Remembering from the very first thing we said about functions was, okay, each input can only give one output, right? So each input, A, for example, can only give me one output. So I can check that by drawing this imaginary vertical line and going through, and it can only intersect the graph once, right, at each point of x. If a vertical line intersects the graph more than once, it's not a function. It still is a thing, it's just not a function, right? Because an input of A gives me B as well as C, right? And so it's not a function because it gives me two outputs. So let's steal this here. Given a graph, we can use the vertical line test to determine if the graph represents a function. But just remember, right, what I said about, well, what we defined a function to be. A function can only have one output for each input, right? And so this vertical line test is just a visual way of checking that, okay? And it says that a curve is a graph of a function if and only if no vertical line intersects the curve more than once. So let's have a look here. And let's just talk about whether it's a function or not. We can talk about the domain too. And I guess we can talk about the range. Fine, fine, fine. Okay. Let me do something wild and crazy here. Yeah. Can you imagine stuffing these next to each other? Ugh. Behave. Okay. I guess that says behaved as, hey, looks pretty good. Gave you some time to have a look at it though, right? And so we're going to use the vertical line test to determine whether the curve is a graph of a function of x. If it is, state the domain and range of the function. Okay? So if it's a function, then we're going to state the domain and the range. So the vertical line test, right? I'm just going to imagine slicing this thing with just a ton of vertical lines. And if at any point this imaginary line crosses this graph more than once, it's not a function, right? So immediately I see that this is not a function, but let's just slow down and talk about, because it's asking us to find the domain, fine, right? The domain is all the input values, but the range we haven't really talked about. The range is all the output values. So here, maybe what I'll do is move them down a little bit and say the domain is all possible input values of x, whereas the range is all possible output values of f of x, but it helps to remember that f of x is just equal to y, right? So it's all the y values are your range. Hopefully that's review, right? So let's go and just draw our imaginary vertical lines here. So is it a function? The first one, yes, right? Because it passes the vertical line test, so there's only one output for each input. For this next one, no, right? Because when I draw a vertical line, I can see that it would intersect more than once. This one's a little bit trickier, right? So here at x equals -1, it looks like, we've got all these possible outputs, right? So all of these outputs happen, making it not a function. right? Because for x equals -1, we've got outputs from -3 to 1, 2, 3, +3, right? Not a function. How about here? This piecewise function, so potentially the first time we've seen a piecewise function in a graph. We've defined it in function notation, but so what happens is it's this horizontal line from -1, -2, -3, from -3 to -1. It's this horizontal line. Okay? The only tricky part where it might not be a function anymore, sorry, is that x equals -1. But because it's inclusive here and exclusive here, we've got a closed dot, open dot situation, it kind of passes the torch, right? And so here, even at x equals -1, it passes the vertical line test because it only has one output. And then, of course, it keeps going, going, going. So this one here is a function, right? Because it passes the vertical line test. So now the domain for the first one, right? We're only finding the domain and range if it's a function. The domain for this first one is all the input values of x. So it's from -1 to 3, it looks like. So from -3 up to +2, including those endpoints because they're a closed dot. So the domain, I'm going to write it in interval notation, is from -3 up to +2. And then for that last one, which is also a function, the domain is from -1 to 3 up to +2 again, right? So inclusive because these are all closed dots, and because it passes the torch here, there's no blip, right? So there's no gap in the values of x that we could put in here, so it's all in the domain. How about the range? The range here is all the possible output values, right? So if we go from the smallest possible output value, that's this guy here, that's at -1, 2, -2, up to the highest point, which is at +2. So the range is from -2 up to +2, and it looks inclusive, so I'm going to use square brackets. Okay. The range for this next one is pretty specific, right? So the range here is strictly at -1, right? And it jumps up here from 0, so an output of 0, all the way to +3. So from 0 to 3. So -1, and how we're going to denote that in interval notation is just -1 to -1 inclusive, right? Because there's no variation there. So it goes from -1 to -1 inclusive. Union, so joint up with the next section. It doesn't include 0, right? Because there's an open dot. So just like we looked at the x's, x is -1, the output would be 0-ish, close to 0, right? But it doesn't include 0. And then the highest output is at 3, including 3 because it's a closed dot. There. Making sure that you recognize that these are ranges, right? The interval notation for the range is your y values. Okay, nice. So, shoot, I am running out of time, aren't I? So, oh no, these ones I let you do on your own. So I would say graph these in Desmos, right? And just figure out, so you can do them algebraically, so using math. But some of them can be a little bit tricky, so use Desmos to check your work and use the vertical line test to figure out if it is a function. Great. Back on track. All right. So we just talked about the domain and the range of a function, right? And so what you can do is, as soon as you see this little calculator image in your notes, definitely use Desmos, right? So here, use Desmos. And I did it in the notes, so I'm gonna just copy. Put it on a fresh page here. Oops. 2.3, getting information from the graph of a function. Okay. So here, these little indicators, just use Desmos for these things, right? Definitely, if you see this little calculator, you have to use Desmos. You don't have to, but you should. Even when it doesn't say to use Desmos to check your work, to try to make that connection between a function and its graph, right? There are even some of those homework problems that really are a lot easier to deal with if you just use Desmos to graph it out. Okay. What I want to talk about though is solving equations and inequalities graphically. So what we could have is we could have something like this. So the solutions of an equation that looks like f of x equals g of x, right? I've got a function equals a function. That's only true where these two things intersect, right? So here, if you've got a function f and a function g, the solutions of f of x equals g of x are at these intersections. And so that's what it says, where the graphs of f and g intersect. So you can use Desmos to find those points of intersection. For inequalities, you can use it too, but it requires a little bit more, more thinking, right? If f of x has to be less than g of x, the output of f has to be less than the output of g. So now here, the region where that's true is all of this, right? So what I want to do is I just want to do one example before I let you go. Let's do 29. So in 29, if we use the notation of, okay, f of x and g of x, then f of x in this case is going to be 16x to the power of 3 plus 16x squared, whereas g of x is going to be x plus 1. Here I'm trying to find f of x equals g of x, so where do they intersect? Here I'm trying to find where f of x is greater than or equal to g of x, right? So A is f of x equals g of x, and B is where f of x is greater than or equal to g of x. So what I want you to do, just to kind of get started with my last minute here, go to Desmos, and let's just graph this thing. 16x to the power of 3, step it down, plus 16x squared. This here is my first function, f of x. And then on the next line, I'm going to have x plus, whoops, not minus, plus 1. That's my next function. So where they're equal to each other are at all these points of intersection. Okay, at x equals -1, -0.25, and +0.25. Where f of x is greater than or equal to g of x, well, that's all these points here. Here, all these outputs are larger than g of x. And same thing from here to here. I'm all out of time, so we'll pick that up next day. But I think that's really good. So have a try of those and see what happens. Okay. Any questions? No. I'll stop this recording. I'll hang back if you have any questions.